In exercise 4, we're going to look at different examples of specific rings, and we're going to investigate what 0 and 1 represent in these rings. So 0 and 1, they are the additive and multiplicative identities in a ring with unity. But if we have a ring that's not integers, that's not real numbers, then what do 0 and 1 actually represent? What do these symbols mean in those contexts? So our first example is going to be polynomials with integer coefficients. So let's look at a few examples of things that are in this ring. 2 plus 3x minus 7x squared, for example, is in that ring. Or minus x plus 4 is in that ring. Constants, minus 14 or plus 28. Those are all things that live in our ring of polynomials in X with integer coefficients. Things that are not in there would be like 1/2 x. That's not in there because it doesn't have an integer coefficient. So what does 0 look like in here? It's the additive identity. And so we are looking for a polynomial that we can add to any other polynomial to just get that other polynomial back. And that's a 0 polynomial. So it's a polynomial that for all inputs x returns just 0 out. So that is our 0 polynomial. What about unity? What does unity look like? That is our multiplicative identity. So it's an element in our ring, it's a polynomial in our ring that we can multiply by any other polynomial and just get that other polynomial back. And that is the polynomial that no matter what you stick in, you get 1 out. So that polynomial is a unity element. Then what does minus 1 refer to? Well, minus 1 is the inverse of unity, and that would be the additive inverse of unity. And so that's the polynomial that when you add it to unity, you get your 0 polynomial out. Well, that has to be the polynomial that returns minus 1, no matter what you stick in. And then finally, what does 3 times 1 refer to? Well, that would be 1 plus 1 plus 1. So unity plus unity plus unity. But unity is the polynomial p of x equals 1. And so 3 times 1 is 1 plus 1 plus 1. Which in this case, viewed as a polynomial, is the polynomial p of x equals 3. So all of these happen to be constant polynomials. Okay, let's look at our second example, part B. So here we are looking at 2x2 matrices with real entries. And what does the additive identity look like? Well, we already looked at examples like this before, so that is the 0 matrix. And what does unity look like? So that has to be a matrix that if you multiply it by any other matrix, you just get that other matrix back. So that is the identity matrix. So if you multiply by the 2x2 identity matrix, any other 2x2 matrix, you just get that other 2x2 matrix back. Okay, then what is minus 1 in this ring? It has to be the additive inverse of unity, and that happens to be the matrix minus 1, 0, 0, minus 1. So that is the additive inverse of our unity that we found before. And then what does 3 times 1 look like? Well, that is 1001 plus 1001 plus 1001, which actually is 3003 in our set of 2 by 2 matrices. Okay, last example. It's just a ring that has 3 elements, x, y, and z, where addition is given in our addition table, and multiplication is given just by the multiplication table. So that's all that we can use to figure out what our 4 elements are. So let's see. So we want to know what is 0 in this particular case. So we need to find, that is our additive identity. So let's look at our addition table and see which of the elements x, y, and z is the identity. So it's something that if we add it to x, we get x back. If we add it to y, we get y back. And if we add it to z, we get z back. And we can see that that is happening. We can see that in the first row or in the first column. So x looks like is our additive identity. Then let's look at unity. So that is our multiplicative identity. Do we have something that if we multiply by everything, we just get that everything back? So something, if we multiply it by x, we get x. If we multiply it by y, we get y. If we multiply it by z, we get z. Yeah, that is happening in the last row or in the last column. So we can see that z is acting like our multiplicative identity. So the third column and the third row of the table just give the elements back that we multiplied by. All right, so then in this case, what does -1 look like? So that would be the inverse of 1, which of course is the inverse, the additive inverse. So we need that's very important. So we need the additive inverse of z. Okay, well, to find additive inverses, let's look at our addition table again. Let me do some cleanup. So it's something that we add to z to get the additive identity. Yikes. Okay, so something that we add to z to get x. What do we add to z to get x? There we go. If I take z and I add y, I am getting x. And I hope that's also happening from the other direction. If I take y and I add z, I also get x. Well, that's good. And so that is telling us that the answer is y. And finally, we were interested in finding 3 times 1. Well, in this case, 1 was z. So we're looking for z plus z plus z. Let's see. So if I take z plus z, clean up. So if I take z plus z, I get y. So z plus z plus z is y plus z. But if I take y plus z, I get x. And so the answer here is x.